Okay, so the first example of an indeterminate bending problem that we're going to solve is this one here. So we have this shaft. It is mounted mounted on three uh, bearings, and it has a load applied to it, a distributed load applied to it between these two bearings. The overall length of the shaft is L. The distance between each of the bearings is L over 2, and the distributed load has a magnitude of W. We're keeping everything generalized here. So if we need to determine the reactions at the supports and then the maximum bending stress induced in the circular shaft. So first off, just redrew this, and we got a free body diagram of our object here. So based upon, we're pressing down on it with W, and we have these three reactions here, AY, BY, and CY. So the way to go about doing this is the easiest way to go about doing this is to treat this reaction here as redundant, which basically means that we treat it as an external load. So our compatibility condition needs to be that the total deflection at that point needs to be 0. And then we just go ahead and we find suitable cases that match what we have for our beam bending formula. So just scrolling down here, the best ones that fit here would be, we've got S1 here. So that's just a simple supported beam with a point load in the middle, which looks exactly like it would be what BY would do, right? And we've also got this S4 here. So it's a distributed load applied to the beam some distance out. So we just and we know that our compatibility condition is that at the center of the beam we need to have the displacement be equal to 0 when we add those two together. So the two different load cases we've got this one here matching S4 Pytel, so that's the distributed load. So the displacement there, that's negative W times 5 L to the fourth minus 12 L to L squared times B squared plus 8 B to the fourth divided by 384 EI. Our B value here is L over 2, so plugging that into here and then kind of factoring out the L to the fourths that result gives us negative W L to the fourth times 5 minus 12 over 4, because the 12 and the half squared gives us 12 to the fourth, plus 8 over 2 to the fourth, or 16. So all that ends up being 2.5. So 5 over 2, which gives us an overall deflection at the center caused by the distributed load of negative 5 W L to the fourth divided by 768 EI. The next one we got here is our point load. So it's pushing, that's the point load is our representation of the effect that the center support will have. So it's pushing up basically in order to counteract the downward movement that would otherwise occur based upon the based upon this load here. This load here would want to move downwards, but it can't because of this support. So there needs to be a certain amount of pushing upwards that occurs. So again, just going from Pytel, that's the S1 case. So we got our point load in the center of the beam. That gives us a displacement in the center of the beam of P times L to the 3 divided by 48 EI. So again, our BY is the P. So just plug in that into there. And then we know that those two displacements, when we add them together, need to be equal to 0. So again, this one's in the case 1. This one's a negative displacement. This one's a positive displacement. So adding those two together, negative 5W L to the 4th divided by 768 over EI plus B times L to the 3rd divided by 48 EI means that we can solve for BY as 5/16 WL or 0.3125 WL. So just go ahead and redraw our free body diagram here, and I'm gonna kind of replace the distributed load with a point load here, so we can use it to help figure out what a reaction is. So again, we've got our two supports. We got the two other remaining supports, the two other remaining unknown supports, AY and CY. So if we take a moment about A, so about this point here, that needs to be equal to 0 because we're still in equilibrium. So that just equals, so 0 is going to be equal to the minus, so the magnitude of this force here, that's W times L over 2. So, it's a distributed load times the length it acts over, so L over 2. And then the moment arm there is L over 4, because, it's centered about that point there. So that's that. Then we got this term here, the 5/16 WL times its distance, which is L over 2. So that is a positive, it's acting counterclockwise. That's a positive. This one here was a negative. This one here would be a positive, assuming we guessed the direction for CY. So that's plus L CY. So just solving for CY, WL over 8 minus WL times 5 over 36 gives us a CY of negative 1 over 32 WL, or to put in decimal terms, negative 0.03125 WL. So from there, we can go ahead and solve for what AY is, just by taking the sum of the forces in the y direction. That's AY minus our load, so minus WL over 2, plus 5/16 WL minus 1/32 WL. So that gives us a value for AY of 7 over 32 WL, or 0.21875 WL. So just put in all that on a free body diagram here. So we can go from there and we can fill out our shear diagram. So our shear diagram, that's, we got at the start, we got this point load pushing up from our reaction. So, from 0, we go up there immediately to that amount, 0.21875 WL. And then we slant downwards. And we slant downwards at a rate of negative W per meter. Sorry, negative W per unit L, not per meter. And that continues for half L. So the difference between here and here needs to be 0.5 L. So this value minus 0.5 gives us that value here. We can also find out where we're going to be crossing the x-axis here, so we can figure out kind of what the base of this triangle is here when we do a calculation for a moment. So that'll, again, 0.21875 WL is our starting point, and then we're moving downwards at a rate of W per L. So we're going to hit X at the same at an L value of 0.21875 L. So anyways, so that's, we get down to here, and then we jump up again because we encounter this load here, our BY reaction, and that bumps us up to 0.03125 WL, and then finally we get to the end and we go down that amount because that is the magnitude of our reaction there. So we started and stopped at the right points. So now we need to find out what our moment diagram is. So again, the key point, we know that these are pinned at the ends. So we know that the moment at either end needs to be 0. So if you start at one end and you get to the other end and it's not 0, you know you've screwed up somewhere along the way. So we can figure out what the change is from here to here, to this value here, just based upon the area of this triangle. So that'll be 0.21875 WL, which is the height of that triangle there. And then the base of that triangle is 0.21875 L. And then divide that by 2 to get our change in moment. So going from there to there, we get 0.0239 WL squared. So that is the magnitude of our moment at this point here. And then next we're going to want to find out how much we drop. Why is this not erasing very well? There we go. We're going to want to find out how much we drop from here to here. So we just need to figure out what the area of this triangle is. So the base here, that's going to be 0.5 minus that. So 0.5 L minus 0.21875 L. And then the height of that triangle is obviously going to be this value here. So minus 0.28125 WL. And divide by 2, because it's a triangle. And that gives us a change in moment of negative 0.03955. So we're going from here, and we're dropping down to this point. Yeah, this distance, this gap here, that's going to be equal to 0.03955. Sorry, WL squared. I forgot to add the WL squared. My bad. Okay, so we got that, and then just got the home stretch here, basically. So from there to there, the change is going to be equal to this amount times this distance here. So 0.5L. 0.5L is the distance, and the magnitude of the shear there is 0.03125 WL. So that works out to a positive change of 0.015625, sorry, 0.015625 WL squared, which is basically exactly what we expected it to do. So we started off at 0, got up here, dropped down, and then moved up back to 0. So one thing to keep in mind here when you're kind of filling in this the moment diagram, keep in mind that you know when the rate of change, right? So I think I've often seen students who do stuff like drawing something like this on their diagrams, but that's we know that in this segment right here, the shear is, it's small in magnitude, it drops to 0, and then it increases in magnitude again. So like the magnitude of the slope is low, hits 0, so it's flat at this point, and then increase, the magnitude increases again. So we're getting something like this. We know that at this point the slope is the lowest because that is where it hits 0. We know at this point the slope is the highest. So the slope should be more here than at any other point on the diagram. It should be still relatively high over here as well, because the slope is directly proportional to the magnitude of the shear, and the slope is equal to the magnitude of the shear. And then from here to here, it's going to be relatively low compared to the other compared to the slopes at the extreme. So but in this section, the slope stays constant because the shear stays constant over here. Shear's constant here, so we get a straight line between here and here. So always keep that in mind. So our deflected shape, we're going to end up with, we've got the moment diagram crossing the line right here, crossing the x-axis right here. So basically at that point, we're going to have an inflection point. So that is kind of the point where the slope changes. Not where the slope changes. So that's the point where the curvature changes. So over here, we've got a positive curvature. So it's curving in a concave manner. And then over here, over this entire area, it's the opposite. It's curving such that it's got a negative moment in that section, so it's curving downwards. It's a frowny face type curvature, whereas on this side it's a smiley face type curvature. So that's our deflected shape. So also one thing we can tell at any point here is that basically on the top of the beam you'll get compression in this section and tension in here. Whereas on the bottom of the beam you'll get tension here, and then compression on the bottom here, because again, that's kind of what happens when you have that curvature. It needs to have, when you have a positive moment, then there needs to be a compressive forces on the top and tensile forces on the bottom in order to curve it into that shape. So just the next thing to do is to figure out what the stress is. So again, we know that the stress is going to be equal to negative times the moment times y divided by I. And again, y there is equal to the distance from centroid. The vertical distance from the centroid. So how far are we from how far up are we, if it's going to be positive, or how far down are we if it's going to be negative when we're looking at our location there. We also have our IZ formula here. So again, that's 1/4 pi r to the fourth. That's just is just the integral of, integral of y squared dA over the area. Again, if you really want to, I'm sure that you could go ahead and do that calculation each time, but I like looking stuff up on tables if it helps me avoid doing calculus. So we get those. Just plug that into the into our stress formula, with our y value being replaced with the r, because we know that it's going to be maximum at the top and it's going to be maximum at the bottom there, depending upon where we depending on whether or not it's a maximum or a minimum maximum compressive, which would be at the top, or a maximum tensile, which would be at the bottom. So that's why I kind of just replaced this with a plus or minus sign here to indicate that we have both going on. And they're the same magnitude because this thing is symmetrical about the neutral axis. Because of that, we know that those magnitudes are the same. If this thing, if it was a weird shape or something, like, I don't know, if it was a shaft but someone had a hole in it or something like that, then the centroid would be shifted upwards a bit. And then in that case, the maximum stress at the bottom, the tensile stress, would be larger in magnitude than the compressive stress at the top. That's not the case here. The case here, they're equal in magnitude. They're just opposite in sign. So again, I threw a plus and minus sign there. So plus and minus mr over ri. So pi over 4 r to the fourth, which, rearranging stuff around, moving the 4 to the top, and then canceling out the r on the top, with the r to the fourth on the bottom, gives us the 4m divided by pi r to the third. So again, our m, the maximum m that we have, that's again just, we got that value there. That's the maximum magnitude of the of the bending moment on our graph. So 0.239 WL squared. So that multiplied by this gives us 0.0304 WL squared divided by r to the third. And then one thing I do like to do is analyze to make sure my units are correct. So again, the W is a force distributed over a length, so force over distance. The L squared, so that's a distance squared, and the R to the third cubed, that's a distance cubed. So again, the force, the distance here cancels out with one of the distances here. The other distance on top cancels out with one of the distances on the bottom, leaving us with force over distance squared, which is a stress level. It's a pressure. It's the type of units we're expecting. So we're good to go there.